Hey everyone, I'm Steven, co-founder of Off-Chain Labs, and we're building Arbitrum, which is a layer 2 scaling solution for Ethereum. And it's also, I know you just heard from Ellie, you probably spoke a lot about ZK rollups. We're an optimistic rollup, and I'll sort of explain what that means. Hopefully it won't be too redundant to what you just heard, and tell you more about where Arbitrum is today and how we do that, and also give you a glimpse into where we're going. So Arbitrum has cheap transactions, which means there's the costs are low, and the way we do that, one way is we don't have expensive cryptography, so there's no really ZK proofs or anything like that. It's really just verifying signatures and the like. The same crypto you've had on a typical layer 1 blockchain. No on-chain re-execution, so we don't need to transactions that happen in layer 2. We don't need to re-execute transactions in layer 1. We're able to do a lot of computation in layer 2 and prove its correctness on layer 1 without ever having to re-execute, even when it's a case of dispute. And we maintain a minimal layer 1 footprint. We derive our security from Ethereum. We use interactive fraud proofs, and anyone can go ahead and validate these proofs. And the security then is rooted in Ethereum. And the basic synchrony assumption that you need, we have a 7-day period to post a fraud proof, which means that as long as you can get some transaction onto Ethereum within that window, or some number of transactions, because our proofs are interactive, then you'll be able to single any honest validator. And because validation, anyone can serve as a validator, anyone can go ahead then and guarantee single-handedly the correctness of the system. Again, the only assumption being that number 1, Ethereum is secure and Ethereum's consensus works, and number 2, that you can get a transaction onto Ethereum during a relatively large period. And then we're also the thing that differentiates Arbitrum from really any other rollup solution that exists today is we're drop-in compatible with Ethereum. We have full EVM support. We're compatible at the bytecode level. We have one-click porting into Ethereum, which means that you take your code from Ethereum code, you take your code that was written for EVM and Ethereum, you take it to you deploy it in Arbitrum, and everything just works exactly like you would expect. You don't need to re-architect your code or change your contract size limits or really change anything. Rollups basically run the spectrum from some require you to use a new language. You probably just heard about Cairo, for example. Others are somewhat compatible with the languages of EVM today at the language level Solidity. Arbitrum goes the furthest and actually gives you the bytecode compatibility, which means we work with all existing languages and developer tooling that uses the basic language support, such as Solidity, any version of Solidity, Viper, anything that compiles down to EVM will just work on Arbitrum. So Arbitrum today is launched in a mainnet beta phase. We launched our mainnet in May, the end of May, and we only opened up to the public a little over 3 weeks ago. And some fun stats here. So we have 1.9 million transactions processed. We have 180,000 unique user accounts that we've seen during this period, 5,500 contract employees, and about 44 billion ARB gas used. ARB gas is our layer 2 gas metric, which is a lot more plentiful and cheaper than Ethereum gas. So, there's no exact 1-to-1 ratio there, but it is a lot more plentiful. So don't get too scared by that number. Okay, so the question then now is then for this audience, which is, so what is the big picture? How does Arbitrum work? And we'll start really high level, and we'll go deeper. So at a very, very high level, Arbitrum is composed of basically, there are 3 parts of the system. There's the inbox, that's the transactions, right? Transactions enter the system, and then those transactions specify some execution or some storage, and that leads to a chain state. And then the chain state also, specifies some outputs, right? So the transactions come in, they do something, then there are outputs to the system. Those could be withdrawals, those could be messages. It's whatever the chain state prescribes. So the high level questions then to understand how Arbitrum works are, number 1, who keeps track of the inbox and the chain state? Number 2, how do we ensure the chain state and the outputs are correct, right? So the whole point of a rollup is to get Ethereum to vouch for your security. If we just, we could just run a side chain and run things separately from Ethereum, and everything will just work and a lot cheaper as well. But the whole point is we want to get Ethereum to vouch for the security by somehow proving its correctness to Ethereum without Ethereum actually validating it. So then the question is, how do we actually ensure the chain state and the outputs are correct? And number 3 is practically how do users interact with the system. And then number 4 is how are ETH and tokens transferred into and out of the Arbitrum chain. Again, we want the same security property of the rollup to apply to the assets, right? So assets that are transferred from Ethereum to Arbitrum and back should have their security derived from Ethereum as well, and the rollup security property should apply. So what is a rollup? And we'll start here then by answering, that first question, of who keeps track of the inbox and chain state. So the transaction data is all on chain. So, and this is true for any rollup, whether it's a ZK rollup or an optimistic rollup. You can think of a transaction as having two logical parts. There's like the actual bits of data of what the transactions are, and then there's the instructions of that those prescribe. Store this, execute this, do this computation. So the actual bits of the data is stored on chain. It's stored as call data on Ethereum, and then the execution and storage are off chain. That happens on the Arbitrum network, and that's done, we'll see later, by Arbitrum validators. And what we want to do is, again, we want the layer 2 to go ahead. We want layer 1, which is Ethereum, to vouch for the correctness of layer 2. And we do that by proving correctness. And I know you just heard a lot about ZK proofs, which is another really great area of development for rollups. But today I'll talk about Arbitrum, and Arbitrum is an optimistic rollup, which means rather than proving validity, we use fraud proofs. That is, optimistically, we post the updates on chain without proof, and then we give a window of time for someone to go ahead and say, no, that's incorrect, and prove that it's fraudulent. And in Arbitrum, the thing that differentiates Arbitrum from any other optimistic rollup is that we use interactive fraud proofs. And we'll see a lot more about those today. And of course, the key property of a rollup, it's secured by the layer on blockchain, and it should have its security derived from Ethereum. And again, this is true. All this is true of really any rollup. These 4 properties, both ZK rollups and any flavor of optimistic rollups. But today we'll dig a lot more deeply into optimistic rollups, in particular Arbitrum and its interactive fraud proofs. So there's the Rollup Protocol, and this is basically the part of the protocol that happens, that is mediated on the layer 1 blockchain. A rollup basically looks like its own blockchain. So here we have what's supposed to be blocks. So you have block number 90, 91, 92. And the Rollup Protocol says Alice, and it can be anyone, anybody could stake. Any validator basically goes ahead and can stake on what they believe is a correct block. So we have basically the ones with check marks. These are confirmed blocks. The system has already confirmed them. Let's say that the dispute window has elapsed and nobody's challenged these. So these blocks, number 91, 90, 91, 92 are confirmed. Now the question is, what is the next block? So Alice goes ahead and she stakes on number 93, and Bob goes ahead and he stakes on number 95. And you see 94 builds on 93, but 95 also builds on 92. So essentially we have a fork here. And again, Bob can be me, Bob can be you. Validator in the full system, validation is completely permissionless and a relatively lightweight process as well. You have to put down a stake, and the point of the stake, the security of the protocols is not dependent on the stake. The stake is basically just to deter, almost like anti-spam, deter people from delay attacks, right? Because each challenge basically it takes time to play out. So we don't want people to challenge frivolously, and that's the point of the stake. But we'll see that anyone who has one stake at hand can guarantee the correct execution of the protocol. So here, Alice and Bob have a dispute, and they need to go ahead and actually resolve that dispute. And there are different ways to do that, but today we'll see how they do that interactively. So how do you prove fraud? So remember that all the inputs are posted directly to Ethereum, and validators make bonded claims about execution. That's what we saw in the last slide. Alice claimed that when you execute this number of steps, you end up with block number 92. And Bob said, no, 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 no. When you go ahead and continue the execution, you actually end up with this conflicting state. So invalid claims can be challenged by anyone. And we saw an example of that where Alice and Bob had conflicting claims, and they implicitly challenged one another, and the protocol enter them into a challenge with one another. And then what we do is we use an interactive challenge to narrow down the dispute. That is, so when Alice and Bob, if we go back here, what is this number 93 and what is number 95? Remember that because all the inputs are on chain, the VM is deterministic, everything that happens is fully deterministic. So Alice is basically saying, hey, I executed the machine n steps, some number of steps, and number 93, this is the hash, and these are the outputs, this is the chain state. And Bob says, no, I executed n steps, and this is the chain, this is the correct chain state. And what basically happens is these are, again, fully deterministic because all the inputs are on chain. But all these are basically n can be very, very, very large, right? They could say I executed 1,000,000 steps, and this is basically what it happens to be. In practice, it can't be too large because we need people to be able to make sure the validators can keep up. But anyway, it can be relatively large. So the question is, so now how does Ethereum know? How does Ethereum again? We want Ethereum to vouch for the correctness of this protocol. So how does Ethereum sort of lift up the hood and say whether Alice or Bob are correct and help them mediate this dispute? So one approach taken by some other optimistic Rollup protocols is to have Ethereum basically just run the entirety of the disputed transactions on chain, but that requires you to keep the disputed amounts very, very small. What we do instead is we have interactive challenges, which you bisect and you basically narrow down the challenge progressively until the only thing that Alice and Bob are disagreeing on is one step of execution, right? They both agreed in this picture. They both agreed on number 92. So they went wrong somewhere, and by basically doing a binary search, we can find the first point of disagreement between them, and then they can resolve that by only using Ethereum to run a single step on chain. In practice, we have many optimizations to the way we do interactive bisections. It's not really bisection, it's really more like K section, where K is like well over 100 in our case. But this is basically the basic flavor of how interactive and fraud proofs works without getting too much detail into the optimizations that we do in production. And so the way that what this looks like is, again, we have some H of S0, and that's the chain state. We'll call that block number 92. That's the state that everyone agreed upon. And then we have Alice here says, okay, I executed n steps and I got this state H of Sn. And then Bob is challenging Alice and saying, no, that is incorrect. And Bob has his own state, but fundamentally, we're just going to focus on Alice's state now because the challenge basically is plays out between an asserter who makes a concrete claim and a challenger who says that claim is incorrect. And so we bisect and we say, okay, what happens if you cut it and only go halfway, right? What happens if what was the midpoint of that? Could you give me the state there? So Alice goes ahead and gives the midpoint there. And notice that she has to separate she has to give both the state of the machine halfway through and also specify where the outputs happen. So you see over here, there was money spent and there were messages sent. These were outputs of the chain. And now Alice has to specify whether those outputs belong to the first half or the second half. And anyway, they go back and forth. In each place, Bob, bisects and Bob challenges one and Alice bisects, and they come down to just a single point of execution. Then all you need to run on chain is this one step. So that's interactive fraud proving, and it might not be clear because the funny thing about fraud proofs, we put so much focus on it, but it's the type of thing that we don't really expect to ever happen, right? So Arbitrum's been running for a few weeks now, and I'm sure when it'll be running for months. I don't expect to see an actual fraud proof in production really ever, because it's just not economical to do. You'll lose a lot of money and for essentially no gain. But we put so much focus in it because the ironic thing is that the fraudulent, the unhappy case of the system, right? It really affects the happy case of the system. How you do the fraud proving really affects how the system runs in the optimistic case. So proving fraud this way allows us to be hyper efficient in the optimistic case. Remember, because we're not re-executing on chain, we're able to make these optimistic claims about really, really large amounts of computation. We can make a single claim about an hour's long of computation. And in the optimistic case, without dispute, all we need to put is the output state and the outputs and the chain hash, and that's it. And everything basically just works, and there's never anything else that needs to happen on chain. And even in the case of dispute, there's minimal L1 cost because it's just a refereeing protocol where you do have a logarithmic many rounds, and we've optimized the logarithm, very, very, very much in practice for the roughly an hour long of execution. It's about 5 rounds of interaction, which is pretty optimized. And so that's just basically posting a hash on chain and calling left or right, and then running a single step of the VM on chain. So a very, very lightweight on chain footprint. It allows us to do things that are much higher gas and contract size limits. Let me give you an example here. And I can mention again how some other optimistic rollups, like Optimism, if you're familiar with the way that they do this, is they actually do this on a per transaction level. They run their disputes happen on a per transaction level. So each transaction has to have basically a checkpoint associated with it on chain. And then the disputes run from checkpoint to checkpoint. But the checkpoints have to be really, really small. And that's why they're on the transaction level, because you can't have, you can't, if you have to rerun things on chain, you can't do more in an Ethereum block than Ethereum allows. So that means is even in the optimistic case, if your dispute approach requires you to rerun transactions on chain, then even in the case where there's no dispute, you can never run more than what Ethereum allows you to run on chain, because you won't be able to dispute it. So your transactions are still inherit Ethereum's limits. You still inherit Ethereum's contract size limit. We're able, by having interactive proving and allowing us to put much more data on chain, we can have contract deployments that use much more gas than is allowed in one Ethereum block. We can have transactions that use much more gas than one Ethereum block allows. And the reason is because even when we dispute, we'll never have to go ahead and run that transaction on chain. Instead, we'll bisect, get down to something very small, and only run that on chain. So it allows us to really break free of Ethereum's limits, not only on a global throughput level, but even on an individual transaction level, individual contract deployment level, and allow us to do things that are much more expensive than you can do even in 1 or 2 Ethereum blocks. And it also, there's interactive fraud proof it leads to a relatively simple implementation. You don't have to have, all the fraud proof is basically just the steps of the VM. We use a relatively simple virtual machine, and it gives us a lot of flexibility. Right now, we are running with full EVM compatibility, but we have flexibility to say change the VM or add VM. We have WASM support that we're working on as well to really add to the user experience and not just limited to what we have today, but supplement that and say how do we make this even better and enrich the current developer environment. So what does this look like for a user? So users talk to Arbitrum nodes and validators. Users basically send in their transactions. That's what's happening on the left side here. A user will send its transaction. This is a user who's not running a node. Of course, any user can run a node themselves. Any user can run a validator, but we'll discuss users who want to either deploy contracts or transact on chain. They'll send their transactions to Arbitrum nodes and validators, and on the right side here, the interface that they'll get EVM contracts. And it happens to be that the virtual machine that Arbitrum running is the AVM, the Arbitrum virtual machine. It's not the Ethereum virtual machine. We have this magical component called ArbOS, which is a compatibility layer that basically does on the fly inside the trustless code translation from EVM bytecode to AVM bytecode, and allows users to have the interface of sending Arbitrum validators and sending the contracts in EVM bytecode directly, and ArbOS basically takes care of the rest. And we'll see more about ArbOS in a bit. So the user experience then is, to summarize, we provide the exact same, the standard JSON RPC endpoint as Ethereum. So it's compatible out of the box with MetaMask, Hardhat, etc. Nodes always know the correct state, and there's no need to trust the validators. If you're running a full node, you will know the correct state. The validators are the ones that are responsible for reporting the state back to Ethereum and engaging in the protocol and challenging another validator. But if you're running a node yourself, you know what is correct, and indeed you know what you can validate, right? So if you see anyone post an incorrect claim, you can yourself go ahead and challenge that and become a validator. So users basically can single-handedly guarantee the correctness, and users can deploy contracts using any version of Solidity or Viper. That's because we have EVM compatibility that's given to us via ArbOS.
I just want to give a few minutes warning, by the way, so we can move on to the Q&A.
Yes. How many minutes was it?
A few minutes.
Yeah. I'm nearly there. So we should be good. So ArboS is the secret sauce here, and ArboS is the layer 2 operating system of Arbitrum, and it does things like I mentioned before. It manages the EVM compatibility at the bytecode level, and it also does other things you'd expect of like a runtime. So it basically takes care of separation of contracts, generalized safe L1 L2 transactions. It takes care of token bridging from Ethereum chain to Arbitrum and back from Arbitrum to the Ethereum layer 1. Also has support for some additional things that were not included in native EVM, like BLS signatures. And the nice thing about it, and BLS is an example of that, it's easily extensible with new transaction types and features that can be added, new batch types, etc. So really, what we've done now today is match the experience to EVM directly. But now the next question is, how do we innovate? How do we make that experience even better for users? How do we supplement that and reduce some of the pain points on Ethereum? And we have, by the nature of the way that we can develop in ArboS, we have a faster development cycle to make some non-controversial changes to that experience. So putting it together then, back to the picture before. So I basically covered this. You have the inbox, the chain state, and the outputs. Again, the inbox are the transactions, which we saw go to Arbitrum validators. The chain state, we discussed the blocks and how the validators go ahead. Right, the chain state is computed via transactions being processed via ArboS in the Arbitrum virtual machine, but then the chain state is summarized on chain by a validator, and then that also specifies outputs like messages or withdrawals, etc. And if you squint a little bit, you'll see a little bit of a more detailed picture here, which is basically this is putting everything we set together, both the off-chain and the layer 1, layer 2 components. So you'll see before the users on the top left, the users we saw before, they talk to Arbitrum nodes and they deploy EVM contracts. And then the Arbitrum nodes in turn talk to Ethereum nodes, right? Because Arbitrum posts all the transaction data on Ethereum. That's the security property of the rollup. All the raw data is posted on Ethereum. So an Arbitrum node directly connects to an Ethereum node, and also Arbitrum nodes need to go ahead and Arbitrum validators go ahead and participate in the Rollup Protocol, which happens on the Ethereum layer 1. So Arbitrum validators will post transactions in the inbox, but also post updated state hashes and challenge other validators and allow the protocol and dispute process to take place. So the users basically have a nice EVM contract that talks to an Arbitrum node, and then the magic happens in this. The ArboS layer here gives the compatibility. AVM architecture is what actually gets posted on chain, and that's what happens. If there's a dispute, it will be a dispute about steps of the Arbitrum virtual machine, the AVM, and that will be refereed by Ethereum with participation from 2 or more Arbitrum nodes. And so who are we? So I'm Steven. I'm a co-founder of Off-Chain Labs. My co-founders are Ed Felton, co-founder and chief scientist. I was a longtime professor at Princeton before joining the company full-time some time ago, and Harry, who's a Kolodner, who was also a PhD student at Princeton with me at the time and is our co-founder and CTO. And we are a growing team today. And shameless plug, please, if you're looking on the job market and looking to do some fascinating research or development work, please come join us. So you can hang out in our Discord, visit arbitrum.io and join our community. We could take a look at our developer documentation if you wanted to start building an Arbitrum, or you can join our team. And like I said, we have great development work. We have all, really some fundamental research work, both about scalability as well as about things about fair sequencing, fair ordering protocols, some of the work that I did at Cornell that we're trying to bring into production as well. So a lot of really great opportunities. And if you're interested, here's a job link, but you can also just reach out to me directly. Happy then to, I guess, move into the next portion.